Good morning, everyone. So, for the last couple of days, we have been discussing about semiconductor materials, the physics of semiconductors, right? About the carriers, how does the carriers move in a semiconductor. So, having built upon all this knowledge, okay, now we are ready to embark on how the knowledge about semiconductors will help in understanding the operations of basic devices, right? So, the first device we are going to start is actually on PN junction, right. So, let's step back and look at the big picture again. Okay, so we discussed the green items here which we have completed so far. Okay, so that's about the basic semiconductors, the materials, the physics, and we looked at the material under equilibrium. We looked at the material under non-equilibrium, that is when we apply some kind of a perturbation to the material by shining light or by applying a voltage, right? What happens to the carrier concentration, right? Now we are going to start see using this knowledge. Okay, we are going to see whether we can explain the operations of some basic devices, right? The devices which are of interest in our course are actually diodes and transistors, right? Because once you are able to understand its operation and the IV characteristics, okay, you can move on using that knowledge as a stepping stone. You can move on to other devices. Let's so we are going to start with this is actually known as a PN junction. Okay, so the why PN junction is so important, right, for semiconductor devices is that, okay, so any semiconductor device, you take any semiconductor device, it will have at least one type of junction, right? So you cannot make devices out of only one type of material, right? There will be a junction somewhere, right? So even if you make a simple resistor, okay, we will see, we have seen earlier, okay, even if it's a simple resistor, if you make an integrated resistor out of semiconductors, you still need some kind of an ohmic contact. Okay, you need to put metal contacts to the semiconductor body to make the connection. Okay, so there you are creating another junction. Okay, so what we know as a metal semiconductor junction. So you require at least one junction. There could be more than one or more junctions to make devices, right? So it could be it's an interface between. So what we call as a junction is, okay, it's an interface between two types of materials. Okay, on one side you have one type of material, on the other side you have another type of material. So there are two types of junctions. Okay, one we call as a homo junction. Okay, so that is a homo junction. That is, so on the both sides of the junction, for example, on the both sides of the junction, you have the material with the same band gap. Okay, with a similar amount of the band gap. Okay, for example, it could be silicon and silicon, or it could be some other material will have identical band gap. The other is known as a heterojunction. So on the other side, okay, they have materials with a different band gap, right? So for example, silicon and silicon germanium, gas and gas. Okay, so they could be closely lattice matched or they may not be lattice matched. Okay, so it has its own effects. Then other thing is a simple metal semiconductor junction, right? On the one side of the junction you have metal, other side is a semiconductor. So this kind of junctions are everywhere, right? So everywhere in a semiconductor device, right? So for example, if you take a billion, like a IC with the billions of transistors, okay, you will have junctions, billions of junctions, right? So where are we using all these junctions? Okay, so for first example is, so if a simple PN junction, like this you might have studied in your +1 or +2. Okay, we used to make rectifiers. Okay, that is to convert from AC to DC or some kind of a power protection, right? Okay, so the rectifiers, okay, use PN junctions. Okay, then also there is something important which is known as ESD protection. That is, okay, so this is electrostatic discharge. Okay, for every IC at the input of this one, okay, wherever the pins are there, you will have ESD protection diodes. The same PN junctions are used, okay, for light emitting devices like LEDs and lasers, right? And the PN junctions are also used in light absorbing devices, okay, where you extract the light and you convert. Okay, this is kind of an energy conversion. You convert from light energy to electrical energy. For example, solar cells, photodiodes. Okay, so they all consist of PN junctions. Once you move, okay, so that may have, okay, at least they require at least one junction, right? But in real device, it may contain more junctions. For example, transistors. Okay, so what I am talking about, at least one junction, is that even a schematic, okay, at least a schematic, okay, a schematic which is used in textbooks, right, it requires at least one junction. On the other hand, if you go to transistors, right, Okay, if you have a schematic which is used in a cross section which is used in textbook, okay, it requires at least 2 junctions. The real device we will see later, okay, real device may contain more than 2 junctions. Then finally, okay, so these are all semiconductor junctions. Okay, so on the other hand, okay, you have actually the simplest of all one is actually an ohmic contact. Okay, so you may think ohmic contact. Okay, so the purpose of the ohmic contact which we saw maybe in the few lectures back. Okay, so that is essentially to the current. Okay, the current should go without any hindrance from the semiconductor to the external world. Okay, so that's an ohmic contact. So the ohmic contact is actually one type of a special metal semiconductor junction. So let us take a simple case. Okay, let's take how does a PN junction diode looks like. Okay, so this is what I am calling as an integrated PN junction diode. Okay, so this is how a diode looks on an IC. Okay, an integrated circuit. That is why it's called integrated diode. So there are two types of devices. Okay, one is an integrated device, other is a discrete device. So discrete device is a standalone device. Okay, you have only one device. On the other hand, okay, integrated devices, okay, you assemble lots of components. Okay, it could be resistors, capacitors, inductors, transistors, diodes, everything on a one solid block. Okay, one monolithic piece. Okay, so on such an integrated block, okay, this is how a PN junction diode looks like. Okay, so for example, so these are the top view. Okay, so top view. Okay, so you can make a contact here. Suppose this is a probe or wiring or a solder wiring or a wire bound. Okay, it will conduct here, another will be connected here. Okay, so these are the two leads. Okay, you will go here. So this is actually known as a top view. Okay, so the top view of a device looks like this one. Okay, then this is actually known as a cross section. Okay, so these two views are very important for maybe all engineering applications and particular for semiconductor device. Okay, you should be able to visualize any device from the top view. How does it, and also you should be able to visualize this thing. How does it in the cross section it looks like. So if you take a cross section along this direction, okay, and this is how the cross section looks like. Okay, so you have this metal. Okay, this is a metal contact. Okay, that is this one which is given in black here, and this metal contact you can see here also, right. So underneath this metal contact you have a P plus region. Okay, that is actually it's a heavily doped P region. Okay, P plus or P plus plus. Okay, that means okay it's slightly heavily doped region, and this is also an N plus region. Okay. So now you can see underneath the P plus, okay, you have an N-type region. N-type region is here. Then the entire N-type region is built upon a P-type substrate here. Okay, so this is how the structure looks like on an integrated. So if you look at the junctions, okay, okay, where are the PN junctions? Okay, you have a one PN junction here. This is one, all right, and this is a 2. Okay, this is another PN junction. There is a third PN. That is not a PN junction. That is an N plus N junction, right? So at least 1, 2, 3. There are 3 junctions are here, even to make a simple diode, right? So these structures, okay, these are shallow trench isolation. That is to on an integrated device, on an integrated chip, you have many devices. So you need to provide isolation. Okay, so this we will see later in the course when we discuss about the VLSI technology. Okay, so this is to isolate. Okay, there could be another device here. Okay, so that is to isolate between these devices. That is the purpose of this shallow trench isolation, right. So this is very important. Okay, the top view and the cross sectional view, right. So you might have seen in textbooks. Okay, we may draw like PN junctions like, okay, this is P here, this is N here, all right. So the real device looks very different from the schematic which is given. So what we are typically doing is that, okay, we are taking a rectangular box here, okay, and this is the P, this is the N. Okay, so this is what goes here. This is what goes here, right. So essentially we are approximating a real device by like this one. Okay, so you may wonder whether that approximation holds good, right. For example, there are some regions here, these regions are here. Okay, so provided if this device is very wide, okay, so you can approximate this 3-dimensional device by like a 1-dimensional device like this one. Okay, so that is a kind of an approximation. Okay, so every engineering problem, it requires some approximation. Okay, you cannot solve everything from first principles. Okay, so this is one kind of an approximation we took. Okay, so the kind of approximations you took, okay, well, it should be valid first of all. Now, okay, so this is the case of a integrated PN junction diode. So, on the other hand, suppose you look at a transistor, okay, if you look at a transistor, so here is an example of a CMOS transistor. So, in the CMOS, okay, so what on the CMOS you have actually a, okay, one N type and a one P type, okay, so this is a symbol, okay, this is actually a NOT gate, okay, so you have a PMOS transistor here, this is an NMOS transistor here, right. So, this is one of the basic gates. It is just a NOT gate, you require two transistors. Okay, so this is how you make a NOT gate. Okay, if you take a cross section here, okay, if you take a cross section in this direction, okay, in this direction, okay, this is how the device looks like. Okay, so this is a PMOS transistor, this is your NMOS transistor, right, and both are sitting on a one single block. So, if you look at the PMOS transistor, okay, so this is the source and drain of the PMOS transistor, this is the source and drain of the NMOS transistor. The NMOS are sitting on a P well here, okay, this is a P well, this is, and here in this case, okay, the PMOS is sitting on an N substrate, okay, so this is one way to make this one, okay, so this is a technology which was used, which is known as a single well and CMOS process, okay, this we used to do till around early 1990s. Right. If you look at the junctions, okay, so this is only for making the transistor. This is only for making the transistor, and this is actually to make the contact to the substrate. Okay, so this is an N plus junction that is to contact the substrate. So you have a P plus region here that is to contact this P well substrate. So if you look at the number of junctions, okay, so you can let's count from here. Okay, this is one junction here, then there is a second junction here, then there is a third junction here, right. And then between the well and the substrate you have another junction, that is fourth junction, this is 5, then 6, then there is a 7, right. So, in this structure itself, okay, you can count 7 junctions, right, that is to in order to create a simple NOT gate, right. So, that is why, okay, so the junctions are everywhere actually. Now, let us look at, okay, so in the real PN junctions, okay, for example, the across the junction, okay, if you look at across the junctions, okay, so it may not be, okay, for example, if you took it here, so this entire P plus has one doping and the N region has another doping, okay, so it's not like the entire P plus is uniformly doped and these N regions are uniformly doped, right, that is very difficult to realize, okay, so it requires more effort to realize uniformly doped regions everywhere. So, typically the real device, okay, the real device has some kind of a doping variation, right, doping variation. For example, in this case, okay, suppose you are making you're starting with a lightly doped substrate, okay, for example, that is this one, okay, your N region is lightly doped and then you are trying to make an N plus or a P plus here. So, typically what happens is that, so this is an N type, this one, and then you are varying the doping, okay, so this was a background doping, okay, this was a background doping here and then you are making another layer. So, there is a doping variation happens, okay, so that is coming from the process whether you are doing diffusion or ion implantation. So, this is a doping variation here, this is a net doping Nd minus Na. So, this is a doping variation here. Then what you do is that, okay, you try to approximate this one by a step profile like this one, right. So, this is, okay, otherwise what happens, this profile, okay, it may have a Gaussian function or a complementary error function, right, that is very difficult to analyze, okay, as we discussed in the previous class, you require some kind of a numerical device simulator to do if you want to analyze the device with the exact doping profile. So, if you want to do it on pen and paper, okay, what do you do is that this is the first approximation, we may assume it like a step junction profile, then it is easy to solve, okay, you can solve the differential equation using pen and paper. This is another case, okay, suppose we do a doping, so there is already a heavy doping, okay, so this is actually slightly larger, this is not to scale. Then if you do an doping on the top of that one, okay, you may get a slightly different shape, okay, so that you may approximate like a linearly graded junction. So, these are some kind of an approximations we make in order to analyze the PN junction. Now, let us see, okay, let us take the case, okay, for example, let us take a simple case, let's take, okay, so you have a PN junction, so you have a uniformly doped P type, okay, so you have a uniformly doped P type body and you have a uniformly doped N type body, alright. So, our goal is to make a PN junction. So, what I am going to do is that, suppose let's take a hypothetical, okay, let's say take a thought problem, so you attach the p plus region and n plus region, right, just like this one. Okay, so you attach this one and form like this one. Whether will you form a p-n junction, right? Let's assume, okay, the interfaces are all clean, okay, there are no dangling bonds and those things are there. Suppose you put it stack these two things side by side. Okay, let us look at the energy band diagram on either side. Okay, first thing is that this is a p-type side, this is n-type side, right? I hope you are all familiar with the energy band diagram. Okay, so this is the conduction band, this is a valence band. The Fermi level is close to the valence band for a p-type semiconductor. For the n side, the Fermi level is close to the conduction edge of the conduction band. And if you look at inside the charge profile, okay, what are the charges you see? This is a p-type. So you have, okay, so you have the holes here. Okay, so these pluses, this is holes, and these are the ionized acceptors. Okay, this is Na minus, right? Similarly, here these are the electrons here, and this is the Nd plus ionized donors, right? So if you look at the concentration here, you have a lot of holes here. Okay, so here on the other hand, and lot of holes, and you have a lot of ionized acceptor impurity atoms here. The other type of, okay, so the donors and the electrons are very, very small here. Okay, so let's assume there are no donors, and the electron concentration is, if you assume these are entirely ionized, so this is n square by, okay, p is proportional to Na minus, and the electron concentration is equal to Ni square by Na, right? So that is why the electron concentration is very, very small here. And if you look at the net charge density is 0. Why? Because it's it's completely neutral, right? This is electrically neutral. That is why the net charge density is 0. Let's look at the n side, right? So it is n-type doping. Okay, so here the majority carriers are electrons, right? So that electrons is actually equal to the Nd plus. Okay, so this will be the same, and the whole concentration are very, very small. Okay, whole concentration here p is equal to Ni square by Nd, that amount. And here also this is completely electrically neutral, right? So what we are going to do is that, okay, we are trying to put these two blocks side by side. Okay, and let's try to imagine what is going to happen. Now I took it both sides and put it side by side like this one. All right. So now the question is, okay, will it remain like this, right? Right. For example, if you look at, okay, this is the energy band diagram. Okay, so you can see the Fermi levels are different. Okay, these are the charge profiles. Okay, so here you have a lot of holes. You have very few holes here. Here you have few electrons. Here you have a lot of electrons. Sorry, this electrons is here. These few electrons, a lot of electrons here. This is a donor concentration. There is an acceptor ion concentration, and everywhere it is electrically neutral. So can this configuration continue to stay under equilibrium? That is a question, right? What is the problem? We have seen here, okay, we have seen some similar case before, okay, that is in a non-uniformly doped semiconductor. Okay, that was not a p-n junction, it was either n-type or a p-type, but there is a doping variation is there. It's a non-uniformly doped. We saw that, okay, so that also it cannot maintain electric neutrality, because there could be, if this net charge is equal to 0, so what happened, there is a huge concentration gradient for the holes here, and there is a huge concentration gradient for electrons here. And similarly, the donor ions also, there is a concentration gradient. The acceptor ions also, there is a concentration gradient, right? So you cannot sustain this concentration gradient like this one, right? So what happens? Okay, so we saw that, okay, finally the system reaches equilibrium. So we saw that one of the major conditions for the system to under equilibrium is that you need to observe that there is no gradient in the Fermi level. Like the Fermi level should be continuous from left to the right, right? On the other hand, okay, you can see here the Fermi level. Okay, this is a Fermi level here. This is a Fermi level here. That is not continuous. There is a sharp gradient here. That is not possible, right? If there is a gradient, we saw that if there is a gradient in the system, okay, that means, okay, there is a current. Okay, the current is proportional to the gradient of the Fermi level. The current should be flowing through the system, right? But if there is a current is flowing through the system, okay, you can do some work. Okay, for example, if you connect it to a resistor or something, you can produce heat, right? So that means, okay, you are doing some work, or you are generating heat or cooling this one, okay, even though the system is under thermodynamic equilibrium. Okay, so that is a violation of the laws of thermodynamics. So that cannot happen. So that means the Fermi level should be continuous. So now the question is, how do you ensure that the Fermi level is continuous? So you have to go back to your principle of detailed balance. Okay, so that is, we saw that every process and its inverse process should balance each other. So in this case, for example, in the case of holes, the hole current, okay, the net hole current should be 0. That is, the drift current due to holes and the diffusion current due to holes, they should balance each other. Same thing for electrons. Okay, the net electron current equal to 0. How does the drift current due to electrons and the diffusion current due to electron should balance each other. So now we can see, okay, we saw that there is a concentration gradient, right? So let us put only those species, okay, where we see a concentration gradient. Okay, in this case there is a concentration gradient of holes. So in this case these are donor ions, and in this case it is electrons, and in this case it is acceptor ions. Then now the question is, okay, you have a concentration gradient of charged particles, right? The question is, okay, which of these particles will start diffusing and how long will it diffuse? Okay, whether it will diffuse till this is same both sides, right? So that is, okay, so you have a starting point. What is the end point? Okay, whether the diffusion will stop and the concentration of all the concentration gradients are 0. Is that going to happen? So the first thing you have to, okay, so there are two types of particles. One is actually the electrons and holes, other is actually the acceptor, the ionized impurity atoms. So at room temperature, their diffusivities or the diffusion coefficients are very different, right? So the diffusion coefficient typically depends upon the mass of the particle. Okay, heavier the particle, okay, so it is difficult to diffuse. So in this case, the electrons and the holes, okay, so they will diffuse at room temperature. The diffusion coefficient of these ionized impurities are very, very small at room temperature. They may be high at higher temperature, but at room temperature we can ignore their diffusion. So that means only the electrons and holes will start diffusing. So what happens is the electrons and holes will start to diffuse at room temperature. So once they start diffusing, they will leave behind the ionized impurity atoms. Okay, the ionized impurity atom they will leave behind. So once they start diffusing, so what will happen? Okay, so the both sides were electrically neutral first. So suppose the holes are moving from this side to this side. So what will happen? They will leave behind a region which are void of holes, but they are full of negatively charged acceptor atoms. The same thing happen for electrons. Okay, once the electron starts diffusing from this side to this side, so earlier this side was completely electrically neutral. So the electrons which are this region, okay, this will create a region of positively charged ionized atoms. So now you can see once the diffusion starts happening, okay, you can see there is a slowly there is a, okay, this is happening very fast, okay, but you can see, okay, you can imagine like a slow motion picture. Okay, what is happening is that there is a buildup of an electric dipole. Okay, electric dipole is, okay, so you have charges which are separated by a distance, right? So on the right side, okay, this is right, okay, on the right side, and this is the left side. The right side you have a buildup of positively charged atoms here, and the left side you have a negatively charged ions here. So if you have charges equal charge of different polarities which are separated by a distance, we know that it will there is a buildup of electric field. So now you can see, so what happens, what is the direction of electric field? The direction of electric field, okay, it starts from a positive charge and it will terminate on a negative charge. That means all the electric field lines are in this direction. Okay, electric fields are in this direction. So if there is more and more diffusion, that means, okay, there will be a slow buildup of electric field. Now you can see what is this direction of electric field. This direction of electric field is in this direction. So the holes are moving in this direction, the electrons are moving in this direction. Now you see what is the direction of what does the electric field does to the diffusing species. The holes will see an opposing electric field. The electrons will also see an opposing electric field. So what is going to happen is that this buildup of electric field, okay, it's going to counter the diffusion phenomena, right? At some point, what will happen is that the electric field in such a manner is that the electric field completely opposes the diffusion of the diffusion of carriers. So then what will happen is that then it will the both phenomena, they are balancing each other, right. So the electric field diffuses, electric field opposes the diffusion. So what happens is that, okay, the diffusion stops, or the rate, okay, or the rate this stops, and what we'll see here is that, okay, it will reach an equilibrium condition. So in such an equilibrium condition, the energy band diagram looks like this one. So it is very okay. So you should understand properly how to draw the energy band diagram at equilibrium. So the thing is that, okay, so what you can do is that, okay, you can draw the n type and p type, n type on. So this, suppose this is a p type, okay, this is a Fermi level. So what you do is that, okay, you draw the Fermi level continuously like this one, right. Then you draw the n type conduction band here, n type valence band here, then you join by a line like this one, okay, it's a smooth curve, okay. So don't make any discontinuities, make a smooth curve, that's how you get this one, okay. So the only principle we are using is the Fermi level should be continuous, that's how you make the energy band diagram, right. And we saw, okay, we saw earlier that if there is any gradient in the conduction band or the valence band, so that means there is a presence of field, okay. So in this case, the field, okay, if you look at the gradient, the slope is negative here, that means the field is in this direction, right. So that is intuitively also, you have a lot of positive charges here, there is negative charge, the field should be in this direction, right. So this is what in equilibrium, this is what happens, okay. So if you look at the energy band picture, so in the n type there are lots of electrons here, in the p type there are lots of holes here. So all these electrons, okay, okay, what it sees, okay, if you look at the energy band landscape, it sees a energy hill, okay. So that means there is a hill here, okay, they cannot go into this side, right. That is because there is an obstruction, okay, that is the p type is on a higher energy side. On the other hand, if you look at the holes here, okay, the whole energy, if you recall, the whole energy increases into the direction. The whole energy, okay, for example, the hole is like this one, okay, the holes will see also an energy barrier in this direction, all right. So it is like, okay, you can visualize like holes are like if you take a bubble or like rubber balls, okay, which are, then you are trying to push the holes, push those balloons or balls inside water. So for example, then it is very difficult to push them further inside the water. So that's the same thing happens, okay, holes cannot flow in this direction because there is an energy barrier for holes, right. So this is the situation under equilibrium, okay, and this is the energy band diagram under equilibrium. So this is very important, the energy band diagram, how this energy band diagram is formed under equilibrium. Now, so this is what happens, okay. So this is the same thing here. So this is the energy band diagram under equilibrium, the Fermi level is continuous, and this is the region, okay. So you see some region here, okay. So in this region, if you look at here, this is where where you have electric field here, this is because this is where the band bending here, okay. So you look at here, there is a dc by dx. So here dc by dx is equal to 0, this is flat, okay. Flat means that is quasi neutral. So this region is electrically neutral, this region is also electrically neutral, okay, that is what here. On the other hand, in the middle region, there is a band bending here. So if there is a band bending, that means there is an electric field. Where is this electric field coming from? That is because, okay, in this region, okay, there are no electrons and holes, okay, that is an approximation what we are doing. So there is very few electrons and holes, the charge density is dominated by the ionized carriers, ionized impurity atoms. So here you have a lot of positive charges, here you have a lot of negative charges. So you can see, that means, okay, if you look at the space charge density, on this side, okay, you have a positive charge, on this side you have a negative charge, right. So you should be comfortable with drawing energy band diagram as well as drawing the charge, the concentration of the charge species. Now the question is, okay, whether you can explain, okay, what is this barrier, okay, what is this barrier, right. So let us try to derive, okay, about this energy barrier, that is energy barrier for electrons and energy barrier for holes, okay. So in this case, the energy barrier for electrons is exactly same as the energy barrier for the holes, okay. This is an example of a homo junction. So here the energy barriers are identical, right. This may not be true for a heterojunction device. Now let us see what is happening, okay. So So, let us take the case of the p-type semiconductor here, the type of n-type semiconductor here, right. So, earlier the Fermi level was here, okay, the Fermi level was here and this Fermi level was here. So, at equilibrium the Fermi level should balance each other, okay. So, the balance each other. So, essentially the amount of band bending required is nothing but, okay, this distance by adding this distance, okay. If you add those two distances, okay, so that is the, so if you keep one side fixed, okay, the other side should shift by that amount to have this the Fermi levels aligned, right. So, that is nothing but, okay, so that is nothing but, okay, what is this distance? This is the distance between the intrinsic, how far the Fermi level is below the intrinsic level on the p side, plus how far the Fermi level is above the intrinsic on the n side. So, if you add these two things, okay, so that will give you the whatever the barrier which is being created. So, okay, for example, let us assume Maxwell-Boltzmann approximation, that is it's okay, so that is, okay, what if you recall, okay, that is EC minus EF is, okay, so the Fermi level is, okay, at least more than 3 kT, okay, let us assume, then you can approximate, you do not need to worry about the Fermi integrals, okay, you can use a Boltzmann approximation. So, then this is the p-type, okay, in the p-type, okay, this is Ni here and this if the Ni is actually is equal to, okay, the whole concentration is Ni times exponential Ei minus Ef by Kt, then Ei minus Ef is actually nothing but Kt of natural logarithm of Ni by Ni, right. So, that is the amount of the how much the Fermi level is away from the intrinsic level. You can do the same thing for here, okay, we assume full ionization, okay. So, the only assumption is that we assume full ionization and non-degenerate doping, that is this one, okay, you can use this Boltzmann approximation. So, this is the number of electrons here and the number of electrons you can assuming full ionization and non-degenerate doping, you can write the electron concentration here. Then you can write the delta between this delta, how far the Fermi level is above the intrinsic level as this one. So, all you need, what we are going to do is that we are going to this side, right. So, if you add these two quantities, okay, that is we are adding these two quantities, essentially it is Kt ln Na by Na and Kt ln Nd by Na, okay. So, that is n, okay, you are adding these two quantities, then becomes a product under the logarithmic expression. So, this actually this, okay, so the energy, okay, so this QVBI, okay, QVBI is equal to Kt ln NiNd by Ni square, alright. So, this is the energy barrier for electrons and holes, right. So, if you have different materials, for example, if different materials, okay, the energy barrier will be different for different materials, okay, even though the doping is the same, right. How does the material, okay, where does the material dependence comes in this, okay. So, this parameter which is known as a built-in potential, okay. So, this has a name, this is known as built-in potential, okay. So, it's a barrier, okay, it's a barrier in energy, or it can visualize the barrier in potential also, right. So, this built-in potential will be different for, suppose you make p-n junctions with a different material, for example, germanium, silicon, gallium arsenide, they will have different built-in potentials. So, which parameter is affecting the built-in potential? It comes from Ni square, right. So, the Ni square is different for different materials. For example, the germanium may have a large Ni square, right, because it has a lower band gap. Then silicon, then gallium arsenide will have a very low Ni square because the band gap is very large. So, you can see the built-in potential will be lower for lower band gap materials for the same amount of doping. Now, okay, we can, okay, so it is very rarely only the junctions will be uniformly doped, okay, and lightly doped on either side, okay. So, if you recall the previous picture, okay, so in most cases the junctions will be, one side will be heavily doped, right, the junctions will be heavily doped one side. For example, here it is an N plus N junction, here it is a P plus N junction, here it is an N plus P junction, here it is a P plus P junction. So, typically in most cases the one of the sides will be heavily doped compared to the other side. So, if one side is heavily doped, okay, so what will happen? Suppose in the case of P plus N junction, okay, in the case of P plus N junction, your Fermi level will be very close to the valence band, okay, or it could be it could be sometimes even inside the valence band, then EI minus EF will be typically half of the band gap, right. On the other side, the n-type side is lightly doped here, so you can still assume the Boltzmann approximation, right. So in this case, the VBI is nothing but, okay, so that is this one. In this case, okay, it is Eg by 2q plus Kt by q ln this one, okay. So we are not, so this is, okay, we are assuming, okay, it is inside, the Fermi level is inside the valence band for a p-type region here. So that is why this term is coming here. On the other hand, suppose it is an n plus p junction, okay, n plus p junction, then you can assume the Fermi level is inside the conduction band or at the conduction band here, okay. So that is why it is Eg by 2 here, okay. But the p-type side is lightly doped, okay, you can still assume the Maxwell, the Boltzmann approximation. So again, the VBI is somewhere here, right. So this type of doping is much more technologically relevant compared to like that equal doping, okay, lightly doped on both sides, right. So if you go back here, okay, that will come, okay, if you go back here, where do you see? So as though I mentioned, there are one side is heavily doped, okay, there is one place where you see lightly doped junction on either side, okay. So that is here. If you look at here, so this is P well, okay, this is a P well on an N substrate, right. So the well to well doping, okay, in a CMOS technology, okay, there you will see lightly doped, okay, on either sides, right. On everywhere else, okay, it would be heavily doped on one side and lightly doped on other side. So this is one region, okay, so this is one region where you see lightly doped on either side. So here is a question, okay, so suppose you may have made a PN junction, and suppose I connect a 1 kilo ohm resistor across a PN junction, right. So if you recall, okay, this one, if you recall the PN junction, where is okay, so this one, okay, if you recall the PN junction, okay, what I am doing is that I am connecting a resistor here, okay, I am connecting a resistor here like this one, right. The question is, okay, will there be a current through this path, and whether there is some joule heating going to happen, okay, in this resistor? That is a question. So you can see there is a, if you look at these 2 points, okay, you have this VBI, okay, you have this built-in potential is here, and if you connect a resistor like this one, okay, will there be, whether that VBI will allow a current through this one, okay, whether the current through this one is like VBI by R, suppose this R, okay, once the current is flowing through this one, whether it will cause, okay, whether it will cause any heating in this one. That is one question. Other question is, okay, suppose you instead of this R, okay, for example, okay, suppose I take this one and I connect a voltmeter here, okay, I connect a voltmeter here, whether what does that voltmeter read, right. So those are the 2 questions, okay, you can think about it. I think I have mentioned this answer before at some context when we are discussing the Fermi level, okay. So if I connect a resistor across a PN junction, does the current flow through it, okay, the options are yes, no, and it depends, all right. So the answer is what? The answer is, this answer is no, all right. The same thing, if I apply a voltmeter across a PN junction diode, do I measure VBI? The options are yes, no, and it depends. So in both cases, the answer is no. Why? That is because there is no gradient in the Fermi level, okay. At equilibrium, the Fermi level is flat. So the voltmeter measures the gradient in the Fermi level. And also the same thing, okay, if you want to power a current through this one, the current depends upon the gradient of the Fermi level. In the absence of a gradient of Fermi level, there is no current in the external circuit, there is neither a current in the external circuit nor the voltmeter reads anything, right. That is the simplest of all answers, simplest, and I would say the most elegant way of answering this question, okay. There is no gradient in the Fermi level, there is period, there is no current in the external loop, and the voltmeter also reads 0 volts. Alright, so now we have we have tried to understand the PN junction in a qualitative manner, right? Now the question is, okay, whether can we do something more, whether can we derive the functional form of the potential and the charge distribution, electric field and all those things. So we saw that the band diagram, okay, it will look like something like this one, right? Okay, we exactly, our goal is to find the functional distribution. Okay, so earlier I explained that, okay, you connect it through a smooth curve without any discontinuities. Okay, let's try to calculate. Our task now is to try to calculate the mathematical expression for that, the variation, right? And we already know, okay, once if you are given the energy band diagram, you can calculate the how does the electrostatic potential looks like. How do you create? Okay, you flip the band diagram. Okay, you flip the band diagram. Okay, so if you look at and take any of the bands, whether it's a valence band, conduction band or mid gap, okay, you will see this variation. Alright, so that gives you the electrostatic potential. Now electric field, okay, the electric field like this one. Okay, so the electric field, if you look at this plot, okay, so if you look at this plot, okay, so and if you take the derivative, okay, E is equal to minus dV by dx, dV by dx, right? So that will, okay, you can see the slope. Okay, initially the slope is, okay, if the slope is very small, then what happens? The slope increases. Then what happens? The slope again decreases. Then it again goes to 0. Okay, so you expect. Okay, so if you look at the function, if you are drawn like this one. Okay, so you expect an electric field something like this one. Okay, there is a peak at the interface like this one, right? And the charge density, if the slopes are different, okay, that means the charge density should be also different, because why? The dE by dx equal to what? Rho by epsilon. Okay, that means here the electric field has a one slope, okay, negative slope, and here I have positive slope. Okay, that means this charge is positive, this charge is negative, right? So then the question is, okay, that is looking at the plot. Okay, on the other hand, suppose you are not given the plot. You are not given the plot. Okay, you are given the band diagram and you are given this picture. Okay, why should the electric field peak at the middle? Okay, can you think about why should the electric field always peak at the middle of the junction, right? That is what we call as a metallurgical junction. That is the interface between the original boundary between the P and the N side. Why should it peak always here, right? For that, okay, it's a simple answer. Okay, it's actually, if you look at, if you have the knowledge of +2 physics, okay, that is enough. Okay, if you look at the charge distribution here, okay, the charge distribution here, so this side is electrically neutral, this side is electrically neutral, right? So you have a region, you have a space charge region, right? The space charge, why it's called, it's a region in space which are full of charges, right? And the net charge density is not 0. So what if you have a lot of positive charges here, you have a lot of negative charges here. Alright, suppose there was only one positive charge and one negative charge. Okay, how does the electric field looks like? Okay, it will be a line, okay, which is starting from positive charge and ending at the negative charge, right? So you can draw the same thing here. Okay, so what you are doing is that I am drawing a line here. Let's assume we draw all the lines here. Suppose the device is very large and all the lines are in one straight lines in this direction. Okay, so I can draw like this one, I can draw like this one. Okay, so that is, so then what I need to do, I need to draw between here and here, I need to draw here and here, then I need to draw here and here, I need to draw here and here like this one, right? If you look at this one, okay, then what you are doing is that you are slowly going from left to right. Okay, and at everything, okay, you are making cross sections. Okay, you are making cross sections like this one. Then you count, okay, at every cross section you see how many lines are crossing that area, that cross sectional area. If you go like this one, okay, so you start seeing the you start seeing the cross, this one, you count the lines. Okay, so you see, you will see a slow build up, you see a slow build up, and that the maximum number of lines are crossing at the interface. Then what again? Okay, it reduces like this one. Okay, so essentially the field is nothing but, okay, it's a number of flux lines, okay, number of lines crossing that interface. So the maximum number of lines are crossing at this point. Okay, so that is the reason why the field peaks at this interface, at the junction between, at the junction. Right. I hope this is clear. Okay, so you should have a physical understanding, that is very important. It's not like you are able to derive something mathematically. You should be able to visualize these things, okay, in your mind. Okay. So, now what we are going to do is that, okay, so we are trying to, our goal is to derive a functional form of the electric field and the electrostatic potential. So, what we are going to do is that, okay, we are going to take an approximation which is known as a depletion approximation. So, the depletion approximation is this one is that, okay, so it's essentially outside the depletion region, outside this region. So, this region, in this region you assume the zero mobile carriers, okay, that means the holes, okay, the n is equal to p is equal to 0, the number of electrons and the hole carrier concentration. So, there you have only ionized impurities, okay, so you have only ionized impurities, right. And also outside the depletion region, the net space charge density, okay, that is 0, okay. So, this region is electrically neutral, this region has only the charge, and we assume there is a sharp discontinuity between these two sides, okay, these two sides, okay. In reality, okay, there could be a small tail here, okay, small tail here, but we are assuming, okay, it is like a perfect rectangle like this one, right. So, if you look at this side, okay, these are all Nd plus and this is Na minus, right, Na minus. So, what you need to do is that, okay, suppose we are interested on this side, okay, so you have, we write the Gauss's law, okay, this is del D by x equal rho by epsilon, okay. So, the rho is nothing but, okay, in this side is Nd plus here, okay, and this is Na minus, okay. If you try to integrate this one, okay, if you try to integrate this one, we can get epsilon x, okay. So, this is electric field, okay, electric field is nothing but, okay, this is electric field, okay, because it is very difficult to, because you have energy also E, okay. So, this is a big epsilon, okay, we are using for electric field, and this is actually permittivity, okay, this is small epsilon, I am sorry, this should be small epsilon. So, what you are doing is you are integrating this one, right. So, what if you integrate, okay, on this side, okay, that is left side, you have q Na minus by epsilon s, that is the permittivity of the silicon plus x plus C1. So, this is one, okay, this is a constant of integration. How do you find the constant of integration? You know the field goes to 0 at this point. At this point, the field should go to 0. At x equal to minus xp, the field should go to 0. So, you put x equal to minus xp, the field should go to 0. That will give you the constant of integration. Once you assimilate the constant of integration, okay, you get this is the expression. Similarly, on the right side, okay, you can do the so this one, okay, rho is equal to Nd plus, okay, q Nd plus on the right side, okay, q Nd by epsilon. If you integrate, okay, so essentially again you get a constant of integration. How do you find a constant of integration? At this edge, okay, at x equal to xn, okay, the field should go to 0. That is, if you put x equal to xn, the field should go to 0. So, now you know the field expression, okay, if you try to plot this one, okay, it has a negative slope, okay, it goes here and you have a positive slope here, okay, this is very important, okay, the slope of this one, the slope of the electric field should match the charge, the polarity of the charge species, okay, if it is negative here, this is negative here, if it is positive, the slope is positive, that means the charge should be positive, that is very, very important, right. The slope, okay, the absolute value of the electric field, but the slope, okay, the slope of the electric field should match the net charge density in that space. So, this is a, alright. So, once you have this one, okay, you can calculate the electrostatic potential on the other side. So, we will alright. So, we can continue this integration, okay, all thing is said, okay. So, you can say, okay, so electric field is equal to minus dV by dx, alright. So, what you do is that, okay, so you integrate this one again, the electric field, okay, so you get the electrostatic potential on the left side or something like this one plus d1, okay, there is another constant of integration, and on the right side also you have another constant of integration like this one, right. So, what we do is here is that, so because it is an electrostatic potential, and what is important is a potential difference between the two sides. So, we assume d1 is equal to 0, and on the other side we know that we already found out what is the built-in potential, right. So, at the other end, okay, we put Vxn as Vbi, okay. So, Vbi, what is Vbi? Vbi we already found out Kt by Q ln Na Nd by Ni square, right. So, this is the form of the electrostatic potential, alright. So, Okay, so maybe I will stop here. We will continue in the next class. So in this class, what we have done, we started the PN junction, right? We try to understand qualitatively what happens, what is the status of the PN junction under equilibrium, how the built-in potential or the energy barrier is formed, right? That is because it's a balance, okay, and at equilibrium the Fermi level should be continuous. Then whatever the drift and the diffusion should balance for electrons as well as holes, right? So there could not be any current flow under equilibrium, okay, because of that current flow, okay. So even if you put a voltmeter across a PN junction, it should reach 0, right, because the voltmeter reads where there is any difference in the Fermi levels. That's very important. Then we derive the functional form of the electric field and the functional form of the electrostatic potential. Please remember what we have done is, okay, it's a very ideal PN junction, that is we assume the doping is uniform on the other side and the dopings are uniformly, okay, it is both regions are uniformly doped. We assume full ionization and we assume the Maxwell-Boltzmann approximation is valid, right. So we will continue in the next class. Thank you.